Hello everyone. The title of this video is Graphing Parabolas with Vertices at the Origin. Alright, so in this video I'm going to be doing examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 12.3, called the Parabola, and I'm under the heading Graphing Parabolas with Vertices at the Origin. And each example I do will be either an example from the reading or a try it problem from the reading or one of the sections at the end, one of the exercises at the end of the section that's related to this particular objective. Okay, so a parabola, like an ellipse or a hyperbola, is one of these conic sections. Right, they show you a picture here. If you take a cone and slice it with a plane, the cross section that'll appear on that plane is in this fashion here, is a parabola shape. Right. And there are some special things about parabolas that we're going to be learning about. There's a special point called the focus, a special line that we'll have to determine called the directrix, and a special segment we'll have to determine called the latus rectum. Right, but here's a picture of a parabola here. Right, and all our graphs will look something like this, right? How the parabola is oriented will change. But there's a vertex, right, which in all the examples in this video, the vertex will be at the origin. And then you may recall from studying quadratic functions, there was an axis of symmetry. Right? Every parabola has a line called the axis of symmetry that's not actually part of the parabola. You'll notice all the dotted stuff here isn't actually part of the parabola. The parabola is the solid U-shaped curve. But the axis of symmetry, right, goes through the vertex, and it's a line of symmetry. If you were to reflect the parabola across this axis of symmetry, it would look exactly the same. Now, on the axis of symmetry, inside the parabola, surrounded by the curve, is another special point called the focus. You see a focus labeled here. And the same distance on the other side of the vertex, so the distance from the vertex to the focus is the same as the distance from the vertex to this line called the directrix. Now the directrix is another dotted line. It's an imaginary line here. And the directrix is always perpendicular to the axis of symmetry. Right, so if you know the axis of symmetry is vertical, the directrix will be horizontal, and vice versa. Right, if the axis of symmetry is horizontal, the directrix will be vertical. Right, and then, as I mentioned, one more thing we're going to have to determine is this segment that contains the focus. Right, you start at one point on the parabola, draw a segment through the focus to another point on the parabola. This segment that is also perpendicular to the axis of symmetry, or you could think about it as parallel to the directrix, is called the latus rectum. Right, this segment containing the focus. And we're going to be also finding the endpoints of this latus rectum. What are the points that are actually on the parabola that are at the ends of this segment? Right. Now, the reason we find the focus of a parabola and its directrix is because of how a parabola is defined. This picture demonstrates the definition of a parabola. A parabola is made up of all these points here on this U shape, right? This one has a vertex at the origin. The focus is at this point called 0p, And if I went p units up for the focus, I'd go p units down to be on that directrix line, which will be horizontal here since the axis of symmetry is the y-axis is vertical. And why we find the focus and directrix is this. If you were to take any point on the parabola, right, they have this point xy here. If you were to take any point on the parabola, find the distance to the focus, the distance to this point 0p here, and then find the distance straight down to the directrix. You go parallel to the axis of symmetry or perpendicular to the directrix. You go straight to the directrix. That distance will be exactly the same as the distance to the focus. See, they're both called d here for distance. So this works for any point on a parabola. You take any point on the parabola, the distance to the focus will be the same as its distance to the directrix. Right, so that's why we're finding this focus and directrix. All right, and they're calling, they're using this letter P here. That will show up in the equations as well. And so they go through and derive the equation for a parabola in standard form. Now, this x squared equals 4py. This is the equation for a parabola like this, where the axis of symmetry is vertical and the directrix is horizontal. And all you need to do is switch up x and y, and you get the equation of a parabola where the axis of symmetry is horizontal and the directrix is vertical. All right, and then they go over that right here in this thing here. So again, if the axis of symmetry is horizontal, if it's the x-axis, then the equation has y squared and not x, right? It's y squared equals 4px. And the value of p will determine where the focus is. Right? And if you know where the focus is, you then also will know where the directrix is. And I'll also talk about, they have these endpoints of the lattice rectum. I think that's a little too much to memorize. But if you know where the focus is and the directrix is, I'll show you how we're going to find the endpoints of the lattice rectum real easy. What you're going to see is that the length of the lattice rectum will just be whatever the absolute value of 4p is, and you can kind of cut that in half and find the lattice rectum that way. But I'll show you that when we actually draw some examples. Alright, and then if the axis of symmetry is the y-axis, or a vertical line, right, if the axis of symmetry is vertical, then the x will be squared and y will be not squared, right? So you have x squared equals 4py. Right? And again, the value of this p will help you determine the focus. And if you know where the focus is, then you can easily determine the directrix, right? It's the same distance on the other side of the vertex. And it'll be a horizontal line if the axis of symmetry is vertical. And once again, they have these endpoints of the lattice rectum, but again, I'll talk about finding those when we draw some examples. And they have all sorts of pictures here. Right, all sorts of pictures here, but we'll be drawing a bunch as well. Right. Okay. So that should be enough description there. So now let me get to the examples. Right, my first example, and in all these examples, we're given an equation that may or may not be in standard form, and I'll write out the standard form most times, at least in the first several examples for sure. And we're asked to graph the parabola, and then identify and label the focus, the directrix, right, this special point, this special line, and the endpoints of that lattice rectum, right, which are a couple points on the parabola. They're the endpoints of a segment, containing the focus that's parallel to the directrix. All right, so the first equation I have here has the y squared but not the x, and notice that the y squared is alone. So this is in standard form. Right? It's y squared equals 4p, right? 4p is just a number, 4 times p, times x. Right? And like I said, if the y is squared and the x is not, that tells me that the axis of symmetry is going to be a horizontal line. In this case, the x-axis. But I'm just going to write axis of symmetry will be horizontal. Right, and I guess you can write this as well. You know, if the axis of symmetry is horizontal, then the directrix, this other special line we'll have to find, the directrix will be a vertical line. And if it's just y squared and just x like this, you know, the vertex is the origin, right? The vertex is the point 0, 0. So you can tell a lot of stuff just from the beginning here with the way the equation is formed. And I'll start drawing some things over here on a makeshift XY plane. And then we'll go to a graphing calculator after to see how if our graph is actually good enough. Alright, so like I said, the origin will be the vertex of the parabola. Right, and I'll label that here. Right, this is the vertex at the origin. The axis of symmetry is going to be horizontal. Now I know they didn't say label it, but I'm going to. So remember, the axis of symmetry contains the vertex, right? We'll cut the parabola in half. And the axis of symmetry is, you know, y equals 0. It's the x-axis. Now, we would like to find now the focus of this parabola and the directrix, right? A special point and line. Remember, the value of p will tell you where the focus is. Right? So here I have, you know, the coefficient of x. This is in standard form. That 24 is equal to the 4p. Right? So the value of p must be 6, right? Dividing 24 by 4. That's a positive 6. So, you know, when we're talking horizontal here, positive means to the right. You know, so the focus is at 6, 0. And I'll put this in a different color because the focus is actually not on the parabola. Right, here's the focus at the point, you know, 6, 0. And notice, you know, that is not a solution of the equation. Right? This is not on the parabola. If you plugged in 6 for x and 0 for y, you'd have 0 equals 24 times 6. That's not true. Right? And then, since, you know, the vertex and focus, you know, the 6 units to the right of the vertex, the same distance on the other side, 6 units to the left of the vertex. 1, 2, 3, 4, 5, 6. That is where the directrix will be. And as I mentioned earlier, if the axis of symmetry is horizontal, the directrix will be a vertical line. Right? I'm going to make this dotted vertical line. It should be perpendicular to the axis of symmetry. Right? So this is called the directrix. And it's a vertical line, so the equation is going to be x equals some number, and it looks like that's x equals -6 here. Right. All right, so now I would now like to find those points, you know, in order to be able to, you know, remember the parabola should be opening around the focus, so I'm going to have a parabola that's opening to the right. And I'd like to find those points, those endpoints of the lattice rectum. Alright, so I'm going to make a little note here. The length of the lattice rectum is going to be the absolute value of 4p. So in this particular example, right, 4p was this coefficient here, right, 24, and that's already positive, right, so the absolute value is 24. So from the focus, just kind of cut this in half and use symmetry. You know, if I want this lattice rectum, which will also be vertical, remember, the lattice rectum should be parallel to the directrix. If I want to find the points on this parabola that are at the ends of this lattice rectum, I go from the focus up 12 units. I'll just do this. That's 12, and then down 12 units. And these will actually be points on the parabola. All right, so I'll label these coordinates, right? So here's 6, 12, and here's 6, negative 12. These are the endpoints, right? The endpoints of the lattice rectum. 6 and then plus or minus 12. And I'll dot that in as well. Right, the lattice rectum is just this, again, it should be parallel to the directrix or perpendicular to the axis of symmetry. There's the lattice rectum, right? And you see that how it has a length of 24, right? 12 and 12. That's what I meant by cutting it in half, 24 and a half earlier. And then check these points. You know, and these points on the ends of the lattice rectum should be solutions of the equation. Look, if x were 6 and y were 12, you'd have 12 squared equals 24 times 6. Well, 12 squared is 144, and 24 times 6 is also 144. So that's true. This is a solution of the equation. And so is this other endpoint, right? Put in 6 for x, negative 12 for y, and again you would get 144 equals 144. All right, and now that I have the vertex and the endpoints of the lattice rectum, you can make a pretty rough sketch of the parabola. Just make it curvy, right? Don't make it pointy. Have it curve, you know, into these endpoints of the lattice rectum and flare out, you know, get wider and wider as you go further away from the vertex. And there you go. There's a rough sketch of this parabola. And that's it. Now, as I mentioned, the whole reason we find the focus and directrix is the following. You know, if you were to take any point, say this point here, or this point here, this point here, this point here, if you take any point on this parabola, the distance to the focus and the distance straight to the directrix, so you go perpendicular to it, those distances should be the same. Right? Now, they're not always going to be the same number, like, you know, maybe these distances are 5 units, and then you pick this point up here, the distances will be greater, but they will be equal. The distance to the focus and the distance to the directrix will be equal. Now, this is a hand drawing, so, you know, that's why I put the little tick marks here, so you know they're equal, because they don't look pretty equal in this picture. But again, it is a hand drawing. I didn't do the greatest job. But let's take a look and see if these points, you know, 6, 12, and 6, negative 12, and 0, 0, are on the equation, and the graph of a parabola opens to the right like this. So I'm going to go to the Desmos calculator, right? Free online graphing calculator at desmos.com. And I'm going to enter the equation that we were given, y squared equals 24x. All right, and you see this parabola, very, very wide parabola, right? A little probably wider than I drew. And, you know, the vertex at the origin, right? And you should be seeing the point 6, 12, right? There's 6, 12, right? You should also have the point 6, negative 12, right there. So it looks like this parabola is the one I drew. All right. Goes to, if you have the origin, if you have the vertex and a point on either side of the axis of symmetry that are correct, then the parabola you drew is more than likely correct. All right. So, great. And this is basically what I'm going to be doing for the rest of the examples. Right. Pretty similar stuff. All right, so my second example is another one where the y is squared and the x is not. So it's in this, and the y squared is alone, right? That's when you're in standard form for these parabolas, the square is on its own side. Right? So this is in this form, y squared equals 4px. Right? So again, just y squared, just x, so the vertex of this parabola will be the origin again. And because it's y squared equals, and then x is not to the second, this is again going to have an axis of symmetry that is horizontal and a directrix that is vertical. But this time I'm just going to write the axis of symmetry is horizontal, right? And you should just know now that the directrix will be vertical and the latus rectum will also be a vertical segment. Right? The latus rectum and directrix should be parallel, both perpendicular to the axis of symmetry. Alright, so I'll start drawing. Again, just a rough sketch over here by hand. If you have graph paper, it might make these nicer, but that's what I'm going to go to Desmos for, just to look at a better picture of these. Alright, so again, the origin, that's the vertex. Right, and that's actually a solution of the equation, right? If x were 0 and y were 0, you'd have 0 equals 0. That's true. And again, I'll put in the axis of symmetry would be the x-axis here, right? Goes as a horizontal line going through the origin. And from here on out, I'm going to label axis of symmetry as AOS, right? So there's AOS, right? Axis of symmetry. Now we can also find the focus and directrix from this, right? It's in standard form, so this coefficient of x over here, negative 16, that's the 4p this time. Right, so the value of p this time is negative. It's negative 4. And when you're going horizontal here, right, the focus should be on the axis of symmetry as well. When you're talking negative, you're going left, right? You go left 4 units. And there's going to be the focus of this parabola at negative 4, 0. Focus at negative 4, 0. Again, that's not a solution. We just need to know where it is so we can tell where the parabola is opening. This parabola will be opening to the left. And if the focus is 4 units to the left of the vertex, the directrix will be 4 units to the right of the vertex and vertical. It's got to be perpendicular to the axis of symmetry. So here is the directrix, and it's a vertical line, so it's x equals some number, and that's x equals 4 here. All right, and now for those endpoints of the latus rectum. So remember the latus rectum, and I'll write this one more time here, has a length of the absolute value of 4p, which in this case 4p is negative 16, so the absolute value of that is positive 16. And the latus rectum should also be vertical. Alright, so just like the directrix. And you cut this in half, and use symmetry. So I'm going to go from the focus, go 8 units up, and 8 units down. Alright, so and those will be endpoints of the lattice rectum, points on the parabola. So from the focus, 8 units up, 8 units down, and I'll label these, here are some points on the parabola. These are actually solutions of the equation, and you can check them out yourself. So -4, 8 is one endpoint of the lattice rectum, and -4, -8 is the other one. And again, I'll make this little dotted line here. This is the lattice rectum for this parabola. And then once you have the vertex and a point on either side of the axis of symmetry, or these endpoints of the lattice rectum, you can make a rough sketch of the parabola. Just start from the vertex and curve out to hit those endpoints, and make sure the parabola just gets wider and wider as you go away from the vertex. Right, so there's a rough sketch of that parabola. And once again, the whole reason we find the focus in directrix is for this. If you were to take any point, this point here, take any point on the parabola, the distance to the focus should be the same as the distance to the directrix, right, going straight to it. Those would be the same. Right. But you don't have to draw that. That's the last time I'm going to draw that picture. Just remember how a parabola is defined that way, using the focus and directrix. All right, and then once again, let's just make sure that these are correct. These points are correct anyway. So it was just, back to the Desmos website. We had y squared equals -16x, and you see this parabola opening to the left. Origins there should have the point -4, 8. All right, there's -4, 8. All right, and then the symmetry, you should see -4, -8 as well. And those were those endpoints of the lattice rectum. So got the vertex, got the endpoints correct. That parabola I drew is good. Right? It matches this one. Okay. So my next example, the first two had a horizontal axis of symmetry, open right or open left. My next two examples will have a vertical axis of symmetry, right, where x is squared and y is not. And this is in the standard form for a parabola because the square is by itself, right? We have x squared equals 4py. So I'll start drawing the information that we get from this. So 0, 0, right, is the vertex, right? The origin is the vertex, and that is a solution of the equation 0 equals 0. Right? The axis of symmetry this time is the y-axis. This time the axis of symmetry, again, I'm just putting AOS is, x equals 0. It's the y-axis is vertical. So then the focus will be on this as well. We just need to find the value of that p. Right now this time the -6, the coefficient of that y, that's the 4p. So p here is a fraction, -6/4, which reduces to -3/2, -1.5. Now when we're talking vertical, a negative number means, down. We're down 3/2. So say here's -1, here's -2, and -3/2 is here. Right? There's the focus. And you know what? I'll just write this off to the side. Then the focus is the point 0, -3/2. 0, p. And then if the focus is, 1.5 units or 3/2 units below the vertex, Here's 1, here's 2, and then 3 halves. Then the directrix will be 1.5 units above the vertex and perpendicular to the axis of symmetry. So the directrix this time is a horizontal line. And that's y equals, right? A horizontal line is y equals some number. That's y equals 3 halves. Okay? And now for the endpoints of the lattice rectum. Right, this time the lattice rectum, I'll just put lattice rectum length, is the absolute value of 4p. 4p is this time -6, so +6. And then the lattice rectum will also be horizontal. Right? It's the parallel to the directrix. So cutting this in half, from the focus, I go 3 units to the right and 3 units to the left, and I get the endpoints of the lattice rectum. These are actually points on the parabola. They actually satisfy the equation, right? This would be the point 3, comma, -3 halves. And then this other point on the other end is -3, -3 halves. And these are solutions. Check them out. Replace x with 3 or -3, and then replace y with -3 halves, and you'll get 9 equals 9 in the equation. And once again, I'll label this little dotted segment here. There's the lattice rectum. And then once you have the vertex and the endpoints of this lattice rectum, you can make a rough sketch of the parabola, and this will be a parabola opening down, going through those endpoints of the lattice rectum. Okay, great. All right, then back on the Desmos site, just to check this out, I'm going to put the equation we were given. X squared equals -6y. See this parabola opening down, clearly vertex at the origin. And then I'll put those endpoints of the lattice rectum in. All right, we had 3, comma, -3 halves. And you see that blue point that just showed up. And then 3, comma, -3, comma, -3 halves. Right, that green point that just showed up. You see those are on the parabola for certain. And they should be, directly across from one another. If you were to make a segment between them, the focus would be on that segment, where the lattice rectum intersects the axis of symmetry. Okay, great. Looking good. All right, so my next example is similar to this. It's another one where the axis of symmetry will be vertical, where x is squared and y is not. X squared equals 8y. So again, this is in this form. X squared equals 4py. So same deal when it's just x squared and y like that. The vertex is at the origin. So here's the vertex, 0, 0. The axis of symmetry this time, because x is squared and y is not, will be vertical. So here, in this example, the axis of symmetry is the y-axis, or x equals 0. The value of 4p is 8 here, right? The 8 equals 4p. So the value of p is +2 this time. So that means, I go up 2 units from the vertex to get to the focus. And so here's the focus. And I'll put the coordinates again over here. The focus of this parabola is 0, 2. And if I went 2 units above the vertex for the focus, go 2 units below the vertex to get my directrix, which will be horizontal if the axis of symmetry was vertical. So this directrix is y equals, -2. That's a horizontal line. All right, then for those endpoints of the lattice rectum, so again I'll write out lattice rectum length is the absolute value of 4p, which is 8 here. All right, and then again the lattice rectum would be horizontal. The lattice rectum should be parallel to the directrix. So from the focus, cut this in half here. I'm going to go 4 units to the right and 4 units to the left. And these will be actually points on the parabola. So focus 4 units right, focus 4 units left. And you can test these coordinates. One of them is 4, 2. The other one is negative 4, 2, right? If you were to plug these values in, you'd get 16 equals 16, which is true. Those are solutions. And here is, once again, the lattice rectum, this segment here, that contains the focus and is parallel to the directrix, perpendicular to the axis of symmetry. And now that I have the vertex and these endpoints in, I can make a rough sketch of the parabola like that. And there's all the points on your parabola. And again, if you take any point on the parabola, take the distance to the focus, it should be exactly the same as the distance to the directrix, straight to the directrix. But I'll leave it to you to play around with that. Okay, and I'm going to also leave the checking at Desmos to you now. If you want to check on Desmos, the graphing calculator, you can. I've already done 3 of them, so I feel like I'm doing all right. The work is good. Okay. Now, the first 4 examples here, the equation I was given was already in standard form. So here's an equation, again, where one variable is squared, the other one is not. Here x is squared and y is not. So the axis of symmetry will be vertical again, like in examples 3 and 4. But this equation is not in the standard form for these parabolas that we've been seeing. Now, to get it in standard form, you need to isolate the square. Get the square alone. See how it's x squared times a quarter? That won't be happening in the standard form for a parabola. So basically I just need to multiply both sides by 4, and you'll have x squared on one side equals 4y on the other. These are the same equation. All I did was multiply both sides by 4. All right. And now we have the equation that is, in standard form. All right, so yeah, it should be simple enough, right? And it's in this form here. X squared equals some number 4p times y. Right. All right, so if that's the case, the vertex is at the origin. Vertex at the origin again. The x is squared, the y is not. So another case where the axis of symmetry is vertical. So again, the axis of symmetry, AOS, is x equals 0 is the y-axis here. The value of p this time is 1, right? 4p is just this number 4. So the value of p is positive 1. And we're talking vertical, so positive is up, right? So the focus is at the point 0, 1. Right, there's the focus. And the directrix, the focus was 1 unit above the vertex. The directrix will be 1 unit below the vertex, and it'll be a horizontal line, right, perpendicular to the axis of symmetry. Right, and the directrix is a horizontal line, y equals, and it's y equals negative 1 here. And then the length, this is also 4. This is also the length of the lattice rectum. Right, the lattice rectum length is 4, and it should also be, horizontal like the directrix. And then cut this in half. That's 2 units. So from the focus, go to the right 2 units, and to the left 2 units, and you get these endpoints of the lattice rectum that are also points on the parabola, right? Also solutions of the equation. So here's the point 2, 1, and here's the point negative 2, 1, and you can check these, make sure that these are solutions even back in the original equation. If I plug in 2 for x, 1 for y, or negative 2 for x, 1 for y, you get 1 equals 1 on both sides. That's true. Again, here I'll label with a little dotted line. Here is the lattice rectum, right? This segment containing the focus that's parallel to the directrix, perpendicular to the axis of symmetry. And now that I have the vertex and these endpoints, I can make a nice rough sketch of the parabola, right? Starting from the vertex, going through these endpoints of the lattice rectum, and there you go. It's this parabola opening up. Great. All right, so here's another one similar to this, where I think my last 4 examples are like this, where the equation doesn't start in standard form, but all I have to do to put it in standard form is get the square alone, the x squared, the y squared. So yes, this is very similar, but this time the y is squared and the x is not. So this time, the parabola will have an axis of symmetry that's horizontal and a directrix that's vertical. So get it in standard form, I would just have to multiply by 36. So here we are in standard form. Y squared equals 36 times x. That's in this form here. Y squared equals 4px. Alright, so if it's in that form, I can recognize right away that it's a parabola with a vertex at the origin. There's the vertex. The axis of symmetry this time will be horizontal. This time AOS, the axis of symmetry is y equals 0. It's the x-axis. It's a horizontal line this time when y is squared and x is not. Alright, then the value of p, well, 4p is 36, and dividing by 4 here, p equals 9. And that's a positive 9, and when we're talking horizontal, positives to the right. So from the vertex, I go to the right, 9 units. So the focus is over here at the point 9, 0. And then if that's where the focus is, the directrix will be 9 units to the left. So it's going to be a vertical line. Here's the directrix. And it's a vertical line, so it has an equation x equals some number, and this is x equals negative 9. Alright, and then this 36, right, that's the length of the lattice rectum. So I'm going to go from the focus 18 units up, so I'll just do this, and 18 units down. Alright, so that way the lattice rectum will have a total length of 36 units. And we get these points on the ends of the lattice rectum that are also, on the parabola. I'll label them. Right, here's 9, 18, and 9, negative 18. Again, check it out. Plug in 9 for x and 18 for y, and you'd get 9 equals 9 in these equations. You'd have 324 equals 324 in this equation, the second one. And here's the lattice rectum, right, the segment, with these endpoints going through the focus parallel to the directrix. And then once we have the vertex, the ends of this lattice rectum, you can make a pretty rough sketch of the rest of the parabola, the rest of the solutions of this equation. Something like that, right? It'll be a parabola opening to the right. And again, I leave it to you to check that all those points are correct and the graph is correct with Desmos if you want. All right, so this next equation, again, another one where it's not in that standard form, one of those standard forms for a parabola, because the square is not by itself. See, it's x squared times 36 equals y. So I would have to divide by 36. So x squared equals 1/36 times y. This is in standard form. It's in that x squared equals 4py form. Alright, so if it's in that form, I know it's a parabola with a vertex at the origin. So once again, vertex at the origin. The x is squared and the y is not, so the axis of symmetry is vertical. This will be the y-axis. The axis of symmetry is x equals 0. And the value of p, right, 4p is 1/36. So I divide by 4, well, or that's the same thing as multiplying by 1/4. So, 1/36 times a quarter, and divide by 4 is just 1 over, and then, 4 times 36, be 144, right? 120 plus 24. So a real tiny number, a real small number. And it's positive, and when we're talking vertical, positive is up. So I'm just going to do this. This isn't great, but this is 1 over 144, let's say. Very, very tiny. And that's where the focus is. All right. And you'll notice that the closer the focus is to the vertex, the wider the parabola will be. I might actually show this one in Desmos just to show you how wide it looks. Yeah, so the focus is at the point 0, 1, 1/44. Right? And the directrix would be that many units below. So here's negative 1 over 144, and the directrix will be horizontal, right, to be perpendicular to the axis of symmetry. And it's horizontal, right? So y equals negative 1 over 144. All right, and then those ends of the lattice rectum, 1/36 was the lattice rectum length, right? That was 4p. And it's the absolute value of 4p is still positive 1/36, right? So the lattice rectum length is 1/36. Now if you cut that in half, 1/36 times a half would be 1/72. All right. So again, this isn't going to be great, but if I go from the focus to the right, 1/72, and the left 1/72, we get those points at the ends of the lattice rectum, these points on the parabola. Right. And I'll label them. Well, you know what? I'm just going to point them out in Desmos. So now I have these points at the ends of the lattice rectum and the vertex. We can make this graph, and I guess I should label the dotted line for the lattice rectum here, but let's actually see, because all these weird fractions, I'll show you we're still correct here. We still have a good parabola opening up. So I'll put the equation we started with. Right, it was y equals 36x squared. You see how narrow that is? Right, and it's because of the fact that p was so tiny. Sorry, did I say wider earlier? The closer the focus gets, it's got a curl around it. The closer the focus gets, to the vertex, the narrower it'll get. Not wider necessarily, but still, there's 0, 0. And let me zoom in a little bit. Now, I guess you could make it look less narrow if you just zoom in close enough, right? You can zoom in as close as you want, and it can look wider and wider if you wish. But anyway, what I wanted to do is zoom in there and just point out these points on the lattice rectum. Right? These are solutions of the equation. One of them was at 1/72nd, comma 1 over 144. Right? And yeah, you see how it's there. It's on the parabola. Just really, really tiny numbers. And the focus is really close to the vertex as well. And the other one was at negative 1 over 72, comma 1 over 144. You see those points are actually on the parabola, right? I'm just zoomed in real close right now. So great. So my drawing was technically good. All the coordinates are correct. All the numbers are right. So let's move on. All right. So I've got one final one where I'll leave it to you to go to Desmos and check that the points are actually on there. And it's another one where x is squared, y is not. So it's going to be opening up or down, and you probably remember from studying quadratic functions that this will be a parabola opening down. But we'll see that when we go through here and put this in the standard form for a parabola that we have now. So I get the square alone by dividing both sides by -9. So we have x squared equals -1/9 times y. Right? There's the standard form, x squared equals some number for p times y. So I recognize that form. I know this is going to be a parabola with a vertex at the origin and a vertical axis of symmetry. So once again, the axis of symmetry is the y-axis, x equals 0. Now the value of p, right, for p is -1/9 this time. So the value of p is -1/36. And when we're talking vertical, negative means down, right? Go down. From the vertex, I go down 1/36 of a unit, right? So there's -1/36, and that's where the focus will be. And then the directrix will be 1/36 of a unit above the vertex, right? And a horizontal line. Horizontal, so y equals positive 1/36. And then the lattice rectum length is the absolute value of 4p, so positive 1/9. Now half of that is 1/18, right? Times a half would be 1/18. So from the focus, I go to the right, 1/18. I'm just going to mark off some stuff here, and then go to the left, 1/18. And here are the points at the ends of the lattice rectum. So 1/18, -1/36, and -1/18, -1/36. And those are the endpoints of the lattice rectum. Again, my drawing's not perfect. It's a hand drawing. If you want to see a better picture, go to Desmos. And then now that I've got the vertex and the ends of that lattice rectum, make a rough sketch of the parabola. Again, it's a parabola opening down as we suspected from the beginning. And there you go. And again, I'll leave it to you to check on some graphing calculator or Desmos that all these points are correct. Alright, and that's it. That's all I got for you today. So I'm hoping that watching me do these 8 examples here help you out in some way when you're asked to graph parabolas whose vertex is at the origin on your own. and thank you very much for watching.